Okay, when a set of T tennis balls was divided into C cans of B balls each, there was one ball left over. Which of the following equation describes the situation? So Margaret, what do you notice about this problem, first thing? What kind of answer choices do you have?
Variables.
When a sample of students take a coaching course to prepare for their scholastic aptitude tests, their scores improve more than a control group who aren't coached.
4/5.
Is this good evidence that coaching improves SAT scores? Chance is involved in assigning students to groups. Maybe the coaching group was made up of students whose next try at the SATs would have resulted in a big improvement anyway, just by chance.
And whatever works is it. It's that easy.
All right, you're about to take the SAT. I'm going to hand out these booklets to you. Don't open them until I say so.
In order to understand whether coaching makes any difference, we need to be able to assess the strength of the evidence that the sample gives. Significance tests help us do this.
1-minute break. So open your books to section 1 and begin. You have 30 minutes.
The first thing we'll learn about significance tests is how to state a null hypothesis and an alternative hypothesis about the population. We'll learn about p-values, the answers given by significance tests. And we'll learn what p-values have to do with the concept of statistical significance, a phrase you'll see used by researchers in many fields of study. One of the most promising products in the long search for a safe, low-calorie sweetener is NutraSweet. Used in hundreds of different foods and beverages, NutraSweet, most people agree, is the best tasting of all the sugar replacements. But maintaining a consistent taste is often a problem, since NutraSweet can lose sweetness after a few months of storage. So when working with a new cola, NutraSweet researchers must make sure the prototype will have a shelf life of at least 4 months. Will this prototype meet this standard? To find out, NutraSweet's sensory evaluation team is preparing for a taste test. The beverage will be evaluated once immediately after it's been made, and then again after 1 month. The difference will be analyzed with a significance test.
Computer, taste your standards first, and then rate your sample. Okay.
This group of 10 panelists has undergone 4 months of daily training. They are about to decide the fate of the prototype cola. When they are ready for their samples, they turn on the red light. Researchers in the kitchen are waiting for the signal. One of the most difficult tasks the panelists learn is how to quantify the enormously subjective attributes they will be rating.
We use these panelists as analytical instruments, and like any analytical instrument, you need to calibrate them. So they're given references of maybe 5 units on the 15-unit scale, 10 and 15. And through a series of examples, they get to know what intensity is associated with all the points on the scale.
After they taste the standards, the panelists are ready to proceed. They taste the cola and rate it in a series of attributes: brown spice, vanilla, sweetness, and many others.
Hi there. Go ahead and sign in number 5. We have 1 sample of cola today.
1 month later, the panelists return. During this time, the cola has been stored in extremely warm conditions to simulate 4 months of storage under normal conditions. The taste test is identical to the earlier one. The same panelists, the same procedures, the same standards, all sources of variability besides the change in the cola have been eliminated. Here are the sample data, the amount of sweetness the cola lost for each of the 10 tasters. The first taster thought the cola lost 2 units of sweetness. The second one thought it lost 4/10 of a unit, and so on. 2 of the 10 tasters thought the cola gained sweetness, and those are the 2 negative values in the data. The average sweetness loss is given by the sample mean. When we do the arithmetic, we see that it's not really a big loss. Is this average loss convincing evidence that the cola is losing sweetness? After all, if we did the taste test again, we would get a somewhat different result. So possibly this one is just due to chance. The way to find out whether or not a result is convincing is to do a test of significance. A test of significance asks, does the sample result, such as x bar equals 1.02, reflect a real change in the cola? Or does it reflect an outcome we might have gotten anyway simply by chance? Significance tests start by stating these alternatives in a specific way. Since we always draw conclusions about some parameter of the population, the first step is to identify the parameter. In this case, it's the population mean, mu. Here, mu is the average loss in sweetness that a very large number of tasters would detect in the cola. The 10 tasters are a sample from this population. The next step is to state the null hypothesis. The null hypothesis says that there is no effect or no change in the population. The sample result is just chance at work. The H0 is the usual shorthand for the null hypothesis. Here, the null hypothesis says that there is no change in the cola's sweetness. We write this in terms of the change in the mean mu. We also need to create an alternative to the null hypothesis, a formal statement that something is going on, that the cola is losing sweetness. This alternative is called, logically enough, the alternative hypothesis, and it's written as HA. Because mu is the population mean sweetness loss, HA is that mu is not zero, but positive. These hypotheses are just a formal way of stating the choices open to us. Either the null hypothesis is true, that is, the sample outcome is just due to chance and does not reflect a real change in the population, or the alternative hypothesis is true. The outcome does reflect a change. Hypotheses are always written in terms of a population parameter, like the mean mu. With the hypotheses in hand, we can now begin to see how significance tests work. Suppose that the null hypothesis is true, that on the average there is no change in the sweetness of the cola. The null hypothesis gives us something to measure our sample result against. We ask, if the null hypothesis is true, is the sample outcome x bar equals 1.02 surprising? If it is, that's evidence against the null hypothesis and in favor of the alternative hypothesis. To find out if our outcome is surprising, we start with what we know about the population of taste testers. We know from long experience that these scores vary according to a normal distribution. The mean of the distribution is the parameter mu. The null hypothesis says that mu is 0. We also know from long experience that the standard deviation of this distribution is about 1. Now we look at the distribution of mean scores x bar for many different samples of 10 tasters. The distribution of x bar is also normal, and its mean is 0 too, the same as the mean for the individual scores. But the distribution of x bar is less variable than individual responses. Here's the formula for its standard deviation. When we do the calculation, it's 0.316. This distribution of sample means shows how sweetness loss would vary if the average loss for the entire population of tasters is really 0. Now we can judge whether any actually observed sample mean score is surprising or not. What if the mean score for our first sample had been 0.3? Would this be evidence that the population mean is really larger than 0? Not really. Since we know the standard deviation, we know that 0.3 is not very far out on the curve. But the actual mean score from our sample was 1.02. That's way out in the tail of the curve, so far out that it would rarely occur just by chance. This is good evidence. An x bar this large suggests that the null hypothesis is wrong, and that the alternative hypothesis, mu is greater than 0, is true instead. We've just established the basic reasoning of all tests of significance. First, find out how the sample statistic would vary just by chance if the null hypothesis were true. Then, locate the outcome of the sample on this distribution. If the actual outcome is very unlikely to occur just by chance, if it is far out in the direction specified by the alternative hypothesis, that's evidence against the null hypothesis and in favor of the alternative hypothesis. This strong evidence led researchers to conclude that the product had in fact changed over time.
And going back, we found that the acidity level wasn't quite right, and that would account for the more rapid decline in the sweetness that we saw. And I
At a
would
strategy
imagine that
session, the results of the taste test are discussed, and a course of action is
I
charted.
don't think you'll be going into an unacceptable level even if you boost the sweetness a little bit initially.
Fine.
Researchers will change the formulation and then test the cola again to see if it retains its sweetness longer. But the process is not over even then. Through rigorous experimental design and data analysis, any attribute of the product can be isolated, tested, and continually improved.
R&D people love to look at millions of things, and we will never stop researching a product. Using statistics, we set the boundaries very quickly, and we understand that outside this parameter we have unacceptability, outside this parameter we have unacceptability, and here's where we're going to live.
Let's recap what we've learned so far about significance tests. To find out whether our sample mean was good evidence for a loss of sweetness, we first assumed that the mean for all tasters really is 0. We then asked whether a sample mean as large as we got was surprising, or whether it would have happened often just by chance. We found that a sample mean of 0.3 would not have been surprising. It would not have been good evidence against the null hypothesis. Our actual sample mean score of 1.02 turned out to be much better evidence. An outcome this large would rarely occur if 0 really were the population mean. The next step in significance testing is to give a number that measures just how unlikely that outcome is. That number is the p-value. Let's suppose, as we did before, that our sample of 10 tasters gave an x-bar equals 0.3. How often would a result this large or larger occur just by chance? Well, that's the probability represented by the area under the curve to the right of 0.3. The probability is about 0.17. That is, 17% of all samples would give a mean score as large or larger than 0.3 just by chance when the true population mean is 0. We'll see in a little bit how to get this probability. What about our actual result? X bar equals 1.02. The probability of a result this large or larger is tiny, only 0.0006. If the true mean were 0, 10 tasters would have an average score as large as this only 6 times in 10,000 tries. An outcome this unlikely convinces us that the true mean is really greater than 0. The p-value is the probability of getting a result as extreme or more extreme than the one we actually got, supposing that the null hypothesis is true. Small p-values are evidence against the null hypothesis because they say the observed result is unlikely to occur just by chance. Large p-values say the observed result is likely to occur just by chance. They fail to give evidence against the null hypothesis. How small must a p-value be to persuade us? There's no fixed rule. But the value 0.05, a result that could occur just by chance no more than 1 in 20 tries, is the common rule of thumb. A result with a small p-value, say less than 0.05, is called statistically significant. That's just a way of saying that the result is not likely to be due to chance alone. This is how we find p-values for ourselves. P-values are just areas under a normal curve, or probabilities given by normal distributions. We calculate normal probabilities by standardizing and using a standard normal table. With our taste test result of x bar equals 1.02, the p-value is the probability that x bar is this large or larger. When we standardize, we first subtract the mean. Here, the null hypothesis says that the mean is 0. So we subtract 0 from both sides of the equation. Then we divide by the standard deviation of x bar. That's the population standard deviation sigma divided by the square root of the sample size. Now we've turned x bar into a standard normal z. In this case, sigma is 1 and n is 10. So we want the probability that z is 3.23 or greater. Because the standardized statistic z says how many standard deviations x bar is away from its mean, we can already see that this is an extreme value. It's more than 3 standard deviations above the mean. The standard table gives the probability below 3.23 to be 0.9994. So our p-value, the probability above 3.23, is 1 minus 0.9994 equals 0.0006, as we said before. Now, what if we wanted to know not only if the cola lost sweetness, but if it gained sweetness as well? The null hypothesis would still be no change. But the alternative hypothesis now allows a change in either direction, so it is mu is not equal to 0. This is what is called a two-sided alternative. The reasoning of the significance test remains the same, with one important change. Remember, the p-value is the probability of an outcome at least as extreme as the result we actually got. With a two-sided alternative, at least as extreme means at least as far out in either direction. So the area below negative 1.02, as well as the area above 1.02, counts toward the p-value. Because normal curves are symmetric, the total is twice the area above 1.02. We know this is 0.0006. So there's another 0.0006 below negative 1.02. The p-value for the two-sided alternative is 2 times 0.0006, or 0.0012. This p-value is slightly weaker evidence against the null hypothesis than our original one. This is just what you'd expect, because a two-sided alternative encompasses more. Is it real or is it chance? Any researcher observing an effect must ask this question. A statistical test of significance gives an answer, but the answer is not a firm yes or no. It's an answer in terms of probability. With significance tests, we're finding out how likely it is that we'd get an effect this large if only chance were operating. Unlikely outcomes, small p-values, suggest that something other than chance is at work. This material has been excerpted from the college television course Against All Odds, Inside Statistics, and re-edited for use in high school curricula. Against All Odds is funded by the Annenberg CPB project. Additional funding provided by these companies and foundations. This adaptation is supported by a grant from the National Science Foundation.